Hi guys, so where we left off, we had found this wave function, which is actually on two lines here, of a hydrogen atom. So this is the wave function of an electron in orbit around a proton, just using the Coulomb potential. One of the interesting things about this wave function is that this electron should stay in this stationary state, right? It should stay in a state that's described by this phi sub nlm, but it doesn't. Collisions or photons colliding with our electron can cause a transition, so a transition from one stationary state to another. And when that transition occurs, the hydrogen electron will give off light, will give off a photon whose energy corresponds to the difference in energy between the initial and the final states of this electron. So each of these wave functions, each of these stationary states, we have an allowed energy that's associated with it. And we can figure out the energy of our photon, and here we'll use a gamma subscript to mean our photon. So the energy of our photon is going to be related to the difference between the energy in our initial state and the energy of our final state. So we remember that for hydrogen, we have a negative 13.6 electron volt energy that is our ground state energy, and we can use that ground state energy to relate the energy of any of our stationary states by that quantum number n. Okay, so if we know the energy of this photon, the next step is to use the Planck formula to relate the energy of the photon to the frequency or wavelength of light. So Planck's formula is going to give us that the energy of our photon is related to Planck's constant times the frequency. And here they use a Greek letter instead of F for frequency here. And we know that as long as we're moving in a medium where the speed of light is c, so if we're moving in vacuum, we can relate the frequency to the wavelength. And here we'll use the standard lambda for wavelength. So if we look at this relationship, we can say that 1 over the wavelength of light equals r times 1 over our final n squared minus 1 over our initial n squared. And this is what I had introduced previously. I'd mentioned it. Rydberg was a mathematician who came up with this formula to describe the frequencies or the wavelengths of the spectrum of hydrogen that he was seeing in terms of just some numbers that he called N1 or N2 and final. And in this case, we can relate this Rydberg formula back to our Planck formula and back to our energy of the photon and our description of the hydrogen atom. And we can figure out that the R in front here, which is known as the Rydberg constant, is related to the mass of our electron. It's related to the constant 4 pi. It's related to the speed of light, h bar to the third, our elementary charge, again, another 4 pi, epsilon 0, so our permittivity of free space. All those numbers together, our Rydberg constant is 1.097, and you can get to more digits if you prefer, times 10 to the 7th. And this is in inverse meters because the Rydberg constant is going to give us inverse meters with that inverse of the wavelength. So that Rydberg constant that was found experimentally by basically fitting an equation to experimental data, we can then relate back to this quantum mechanical solution that we come up with using the solution to the Schrodinger equation. We can also describe a couple different possibilities for our spectrum of hydrogen. So other possibilities for our spectrum of hydrogen, let's get to a fresh page. We can describe, for instance, transitions to our ground state. So N1 would be our ground state. Those transitions are known as the Lyman series. And because that transition is kind of a large transition, because the spacing from the ground state to the first excited state is pretty large, and then to the second even larger, you can picture it. The Lyman series actually has a higher energy. It would be in the ultraviolet region. So it would be ultraviolet light. Our transitions to our final state of n equals 2 would be our first excited state. And they are known by the name Balmer series. So the Balmer series is actually the series that Rydberg was using to do his calculations and come up with his empirical formula. They are visible light. And then there's also a name for transition to our second excited state, which would be a final state of n equals 3. And that second excited state has the name the Paschen series. So these are all named after various scientists. And because this is lower energy still, because there is a smaller gap between the third excited state and higher states, those are infrared. At room temperature, most hydrogen is in ground state. So that's why looking around you are looking at a gas of hydrogen, you're not seeing it glow. But in, say, a hydrogen lamp that we would have as an example in class if we were face to face, you get your hydrogen into excited states with an electric spark, and then after they are in that excited state, they begin to cascade down to the ground state, or the first excited or the second excited, and you can use a prism or diffraction lenses to see these different excited states. Now, there is a picture in your book that gives you these excited states, that gives you a visual of what these states look like, or one way to look at it. So one of the ways to look at it is to look at kind of a ladder, where n equals 1, you've got that negative 13.6 eV energy. And then at n equals 2, I'm just going to write that it would be negative 13.6 eV over 2 squared, or over 4. And then at n equals 3, it would be your negative 13.6 over 9, right? And on over 16 for n equals 4, over 25 for n equals 5. And so these get closer and closer together. So when you have an electron in an excited state, say it's in the n equals 2 state, and it falls to the n equals 1 state, it emits that photon, right? So it ejects the energy that is equal to the energy of that photon to go exactly from the n equals 2 allowed energy to the n equals 1 allowed energy. And since we're going down here to n equals 1, that is what we call the Lyman series, right? So any of these that head down to n equals 1 would be our Lyman series. Let's switch colors. If instead we were headed to our n equals 2, this would be our Balmer series. And same for going to the n equals 3, the second excited state, that would be our passion series. So that's a good place to pause, and when we pick up next time, we'll start talking about angular momentum.